We begin with a simple question, grounded in time rather than imagination. In one human lifetime, how far could a person actually travel through space? Not in stories or distant futures, but within the quiet limits of a real human body, living one ordinary span of years. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. If you'd like, you can share in the comments where you're listening from tonight. And if this kind of calm, science-led exploration helps you rest, a gentle like or subscription quietly supports the channel. Now let's begin and explore the science of how far a human could travel through space in one lifetime. To answer this question clearly, we first need to agree on what a lifetime means in physical terms. For most humans, this is somewhere between 70 and 90 years. Not an abstract measure, but a fixed amount of time in which a body breathes, metabolizes energy, repairs itself, and gradually ages. Every journey we discuss tonight is limited by that clock. Distance in space is not mainly limited by courage or intention. It is limited by speed. Distance is simply speed multiplied by time. This may sound obvious, but it is the most important idea in the entire discussion. No matter how advanced the technology, no matter how empty or vast space appears, distance only accumulates while something is moving. And it accumulates slowly unless speeds become extreme. It is also important to recognize that humans are already moving through space, even when we feel still. Right now, as you rest, Earth is rotating beneath you. At the equator, this rotation moves you at about 1,770 kilometers per hour. At the same time, Earth is orbiting the Sun at roughly 30 kilometers per second, and the Sun itself is orbiting the center of our galaxy, carrying the entire solar system along with it. So even a person who never leaves their bed will travel an enormous distance through space over a lifetime, simply by being attached to Earth. This kind of travel is passive. It requires no fuel, no rockets, and no awareness. But it still counts as motion through space, governed by real physics. However, this is not usually what people mean when they ask how far a human could travel through space. Most people imagine active travel, choosing a direction, accelerating, leaving Earth behind, and moving outward. To understand that kind of journey, we need to separate motion that happens naturally from motion that humans control. The moment a human leaves Earth, the situation changes. The body enters an environment with no air, intense radiation, extreme temperatures, and long periods of isolation. Movement now depends on machines that must carry energy, fuel, shielding, food, water, and air. Every kilogram added to support life makes it harder to accelerate, and every increase in speed requires a large increase in energy. This is why space travel is not mainly a problem of navigation. We know where things are. It is a problem of physics and biology working together. How fast can we go without destroying the human body? How long can we survive while going that fast? And how much energy can we realistically carry or generate along the way? Tonight, we will move slowly through these constraints. We will start with familiar speeds, then step outward, from Earth to orbit, to the Moon, to the planets, and finally to the edge of what a single human lifetime allows. We will not rush ahead. Each step builds on the last. For now it is enough to hold one idea gently in mind. Space is not hard to aim at, but it is very hard to cross. And the distance a human can travel is written quietly in the balance between time, speed, and the fragile biology that makes us human. Before we can measure how far a human could travel through space, we need to be precise about what travel actually means in scientific terms. Without that clarity, distances become misleading and comparisons lose meaning. In everyday life, travel usually implies control. You decide to move. You choose a direction, and you expend energy to change your position. Walking, driving, flying. These are all examples of active travel. Space travel, in the strict sense, follows the same principle. It requires intentional motion relative to a reference frame, usually Earth, the Sun, or another celestial body. However, physics reminds us that motion is always relative. There is no absolute stillness in the universe. A person standing motionless on Earth is still moving through space because Earth itself is moving. This creates two very different categories of space travel: passive motion and active motion. Passive motion is movement you experience without choosing it or controlling it. Earth rotates once every 24 hours. It orbits the Sun once every year. The Sun orbits the center of the Milky Way over hundreds of millions of years. As long as you remain on Earth, you're carried along by all of these motions. Over a lifetime, this adds up to an enormous distance, billions of kilometers, even if you never leave the ground. But passive motion does not let you decide where you go. You cannot use Earth's orbit to reach another planet of your choosing. You cannot step off Earth's rotation and drift somewhere else. Passive motion moves you, but it does not transport you in a navigational sense. When people ask how far a human could travel through space, they almost always mean active travel. They are asking, how far could a person intentionally go, using technology, within one lifetime? This distinction matters because active travel is much more demanding. To move independently through space, you must overcome gravity. Earth's gravity holds the atmosphere, the oceans, and every human body tightly to its surface. Escaping that pull requires a large amount of energy delivered in a very short time. That energy must come from fuel, and fuel has mass. Carrying fuel makes escape harder, creating a self-reinforcing challenge. Once free from Earth's gravity, the rules change, but they do not become easy. In space, motion is efficient once achieved. Objects keep moving unless acted on by a force. But reaching high speed in the first place is costly. Every increase in speed requires energy, and doubling speed requires more than double the energy. This relationship is one of the fundamental limits on space travel. Another important clarification is direction. Traveling through space does not automatically mean traveling outward from Earth in a straight line. Much of space travel involves orbiting, moving sideways fast enough to continuously miss the planet beneath you. Orbiting is a kind of perpetual falling, where forward speed prevents collision. This allows long-distance travel over time without constantly firing engines. For example, astronauts aboard the International Space Station are clearly traveling through space. They circle Earth roughly once every 90 minutes, covering tens of thousands of kilometers per day. Yet they remain close to Earth, bound by its gravity, and unable to reach the Moon without a major change in speed. So when we ask how far a human can travel, we must specify not only time, but mode of motion. Are we orbiting? Are we escaping? Are we coasting? Are we accelerating continuously or only briefly? Each of these choices dramatically changes the answer. For the rest of this exploration, we will focus on active, intentional travel, movement where humans use technology to change their trajectory and distance from Earth. Passive motion will remain in the background, quietly reminding us that even stillness contains motion. but it will not define the limits we are measuring. With that clarity in place, we can now turn to the most important constraint of all, the length of a human life itself. To understand how far a human could travel through space, we need to pause and examine the most fixed variable in the equation: time, specifically the length of a human life. In physics, time is often treated as flexible. We talk about seconds, years, or millions of years with equal ease. But for a human traveller, time is not abstract. It is measured by biology. Cells divide a limited number of times. Organs slowly wear down. The nervous system accumulates stress. No matter how advanced our machines become, the human body sets a firm upper limit on how long a journey can last. For most people today, an average human lifetime is around 75 to 85 years. Some live longer, some shorter, but this range is a realistic baseline. From a space travel perspective, this entire span cannot be devoted to travel. A person must be born, grow, train, and prepare. Even astronauts typically reach space after decades of education and physical conditioning, so the effective travel window is smaller. If a human were to spend time in space, it would likely occur during adulthood, perhaps between the ages of 30 and 70. That gives us roughly 40 years, about 1.26 billion seconds, as an optimistic upper bound for active travel. This number is important because distance in space grows linearly with time, but only if speed is constant. 40 years sounds long in human terms, but in cosmic terms, it is extremely brief. Light travels nearly 40 trillion kilometers in that time. Human-made spacecraft do not. Another biological factor is aging itself. Even if a person could remain alive for 80 or 90 years, the body changes significantly over that period. Muscle mass declines, bone density decreases, the immune system weakens. In microgravity, these effects accelerate. Astronauts lose bone density and muscle strength much faster in space than on Earth, even with exercise. Radiation exposure also accumulates with time. Outside Earth's protective magnetic field, high-energy particles from the Sun and distant cosmic sources damage DNA. Over months and years, this increases cancer risk and degrades tissues. Shielding helps, but shielding adds mass, which limits speed. So time is not just a neutral container in which travel happens. Time actively erodes the traveller. This makes human space travel very different from robotic exploration. A probe does not age. It does not need sleep. It does not suffer bone loss or psychological stress. If a probe lasts 50 years, that is simply an engineering achievement. For a human, 50 years in space would represent most of an entire life, spent under constant strain. Because of this, space agencies plan human missions in months and years, not decades. A 6-month stay on the International Space Station is already considered long duration. A 1-year mission is a major physiological experiment. Missions lasting multiple decades remain far beyond what we know how to support safely. When we ask how far a human could travel through space in one lifetime, we're really asking how much distance can be accumulated before biology says stop. That stop may come from aging, illness, radiation damage, or psychological limits, long before the theoretical end of life. This is why time must always be treated as a budget. Every year spent accelerating is a year not spent coasting. Every year spent coasting is a year of exposure. And every year spent exposed reduces what comes after. As we move forward, we will keep returning to this quiet constraint. Space is vast, but time, human time, is narrow, and all distances we calculate must fit inside that narrow span. Once time is fixed, speed becomes the deciding factor in how far a human can travel through space. Distance, in its simplest form, is speed multiplied by time. If time cannot be stretched very far, then speed must increase for distance to grow. This is where space travel encounters its hardest limits. Speed in space is not about moving fast for a moment. It is about sustaining motion over long periods. A brief burst of acceleration can move a spacecraft out of orbit, but it does not carry it far across the solar system. Long-distance travel requires either very high speed maintained over years, or repeated acceleration events that gradually increase velocity. On Earth, speed is limited by friction and air resistance. In space, those forces mostly disappear, but gravity replaces them as the dominant obstacle. Every planet, moon, and star creates a gravitational well. To climb out of one well and into another requires energy. That energy must be carried or generated, and both options have costs. The most important idea here is that accelerating mass requires energy, and energy has weight. Chemical rockets, which are the only technology that has carried humans beyond Earth orbit so far, must carry their own fuel. Most of the mass of the rocket at launch is fuel used just to lift the remaining fuel. This creates diminishing returns. To go a little faster, you must carry a lot more fuel. Even once a spacecraft reaches high speed, increasing that speed further becomes extremely expensive. Doubling speed does not simply double energy requirements. Because kinetic energy scales with the square of velocity, small increases in speed require large increases in energy. This relationship quietly enforces the universe's speed limits. For humans, there is another constraint. Acceleration itself stresses the body. High acceleration can cause loss of consciousness, damage blood vessels, and strain organs. Humans can tolerate only a few times Earth's gravity for short periods. Continuous high acceleration over days or weeks is not survivable with current understanding. This means that human spacecraft accelerate gently compared to missiles or probes. Acceleration is spread over minutes or hours, not seconds. Once the engines stop firing, the spacecraft coasts at a fixed speed. That cruising speed determines how quickly distance accumulates. To build intuition, consider familiar speeds. A commercial jet flies at about 900 kilometers per hour. At that speed, it would take over 40 years to reach the moon, longer than an entire working lifetime. And that assumes a straight line and no gravity to fight. Even Earth's orbital speed around the Sun, about 30 kilometers per second, feels fast. But at that speed, it would still take more than 4,000 years to reach the nearest star system. These numbers are not meant to discourage curiosity. They are meant to anchor it in reality. Speed is not something we can casually increase by clever engineering alone. It is constrained by energy, mass, and biology all at once. Every design choice trades one limitation for another. More fuel increases mass, more shielding increases mass, more life support increases mass, and more mass reduces achievable speed. So when we ask how far a human can travel in one lifetime, we're not just asking how fast a spacecraft can go in theory. We're asking how fast a spacecraft can go while carrying a living human, keeping them alive, sane, and healthy for decades. As we move forward, we will start to look at real speeds that humans have actually reached, not in imagination, but in recorded history. These will give us solid reference points as we continue outward. Before we move fully into space, it helps to anchor our understanding of speed in experiences that are familiar to the human body. These everyday speeds are slow by cosmic standards, but they provide an important baseline. They show just how dramatically space travel departs from ordinary motion. A relaxed walking pace is about 5 kilometers per hour. At this speed, a person walking continuously for an entire day would cover roughly 120 kilometers. Over a year, if walking never stopped, that distance would grow to about 43,000 kilometers. Over a lifetime of 80 years, uninterrupted walking would amount to roughly 3.4 million kilometers. That number may sound large. On Earth it is, but in space it is almost nothing. The average distance from Earth to the Moon is about 384,000 kilometers. At walking speed, it would take nearly 9 years to reach the Moon, assuming no need for rest, food or sleep, and assuming gravity did not pull you back. Driving increases speed by an order of magnitude. A car travelling on a highway might average 100 kilometers per hour. At that speed, a person could reach the Moon in about 160 days if a road existed. Over a full lifetime of constant driving, the distance travel could reach around 70 million kilometers. This is enough to cross Earth's orbit around the Sun, but not much more. Mars, at its closest approach, is still tens of millions of kilometers away, and this assumes constant speed with no interruptions, which is not physically or biologically realistic. Flying takes us a step further. A commercial jet travels at roughly 900 kilometers per hour. That is fast enough to circle Earth in less than 2 days. Over 1 year of continuous flight, a jet could cover nearly 8 million kilometers. Over a lifetime, perhaps 600 million kilometers. Now we are approaching distances that begin to matter within the inner solar system, but even here, limitations remain. The Sun is about 150 million kilometers from Earth. At jet speed, it would take nearly 20 years to reach the Sun's orbit, not the Sun itself. And this ignores gravity, fuel limits, and the impossibility of flying a jet in space. These familiar speeds highlight a key idea. Human intuition about distance evolved on a planet where everything is close by cosmic standards. Walking, driving, and flying feel fast because Earth is small. Space reveals how narrow that perspective is. Even the fastest speeds we encounter in daily life are far too slow for meaningful interplanetary travel. They do not fail by a small margin. They fail by factors of thousands or millions. This realization is not meant to feel overwhelming. It is meant to gently recalibrate expectation. Space does not yield to incremental improvements. It requires entirely different regimes of motion, speeds so far beyond daily experience that they must be learned intellectually rather than felt. As we continue, we will leave behind these everyday speeds and move into motions that humans experience only indirectly. The speeds of planets, orbits, and spacecraft. These are the speeds that begin to shape realistic answers to how far a human can travel. Before any human-built spacecraft enters the picture, Earth itself is already doing most of the moving. This motion is steady, predictable, and powerful enough to carry every person on the planet through enormous distances over a lifetime. Earth rotates once every 24 hours. At the equator, this rotation moves the surface at about 1,670 kilometers per hour. At higher latitudes, the speed is lower, but the motion is always present. You do not feel it because everything around you is moving at the same rate. Floors, air, oceans, and bodies all share the same rotational frame. This rotation alone adds up. If you lived near the equator and remained there for 80 years, Earth's spin would carry you more than 1 billion kilometers through space. That distance is real, it is measurable, and it happens without effort or awareness. But rotation is only part of the story. Earth also orbits the Sun. This motion is much faster. Earth travels around the Sun at roughly 30 kilometers per second, which is about 108,000 kilometers per hour. This speed is consistent throughout the year, tracing a nearly circular path with a radius of about 150 million kilometers. At this speed, Earth completes one full orbit annually, covering a distance of about 940 million kilometers each year. Over an 80-year lifetime, that becomes roughly 75 billion kilometers. This is already far greater than anything a human could actively travel using current technology. And even this is not the full picture. The Sun itself is moving. Our solar system orbits the center of the Milky Way galaxy at approximately 220 kilometers per second. This motion carries Earth, the Moon, and every human ever born around the galaxy on a vast, slow arc that takes about 230 million years to complete. Over a single human lifetime, this galactic motion adds tens of trillions of kilometers to the distance you have traveled through space. When these motions are combined, Earth's rotation, Earth's orbit, and the Sun's galactic orbit, a person who never leaves the planet still travels an immense distance through space. In purely physical terms, the answer to how far does a human travel in one lifetime is already staggering. But this kind of travel has an important limitation. It is not directional in a meaningful way. You do not choose where you go. You do not approach a destination. You trace repeating paths through space, looping around larger and larger centers of gravity. This motion also cannot be used to reach other stars or planets intentionally. Earth's orbit keeps you bound to the Sun. The Sun's orbit keeps you bound to the galaxy. These motions are stable and closed. They do not carry you outward into interstellar space. So while it is true that humans travel vast distances simply by existing, this does not help answer the practical question most people are asking. Passive motion gives us distance without access. It gives movement without arrival. This distinction matters because active space travel must add velocity on top of these existing motions. To leave Earth, you must move faster than Earth's escape velocity. To leave the solar system, you must exceed the Sun's gravitational hold. Each step requires intentional acceleration beyond what natural motion provides. Still, Earth's motion is not irrelevant. Spacecraft launches take advantage of it. Rockets launched eastward near the equator gain a small but meaningful boost from Earth's rotation. Interplanetary trajectories are planned around Earth's orbital motion to minimize energy use. In this way, Earth's constant movement becomes the starting point for every journey. It is the moving platform from which all human space travel begins. As we continue, we will shift from motion that carries us automatically to motion that must be earned, with fuel, engineering, and careful planning. If we pause here and add together the motions we've already described, a surprising picture emerges. Without launching a single rocket, without leaving the surface of Earth, a human being travels an extraordinary distance through space over the course of a lifetime. Let us gather the pieces calmly. First, there is Earth's rotation. Depending on where you live, this contributes hundreds to over 1,000 kilometers per hour of motion. Over decades, this adds up to billions of kilometers traced through space, even though the path loops back on itself every day. Second, there is Earth's orbit around the Sun. This is the dominant contributor. At roughly 30 kilometers per second, Earth carries every person around the Sun once per year. Each orbit covers nearly 1 billion kilometers. Over an 80-year lifetime, this alone amounts to about 75 billion kilometers traveled. Third, there is the Sun's orbit around the center of the Milky Way. This motion is slower in angular terms but much faster in linear speed. It carries the entire solar system through the galaxy at over 200 kilometers per second. Over a human lifetime, this adds tens of trillions of kilometers more. If we define travel strictly as distance moved through space, then the answer to our original question becomes almost trivial. A human travels farther through space in one lifetime than any spacecraft we have ever built. Not because we are fast, but because we are passengers on a very fast system. But this answer feels unsatisfying, and for good reason. This kind of distance does not represent exploration. It does not represent choice. You cannot decide to stop Earth's orbit and step off near Jupiter. You cannot alter the Sun's galactic path to visit another star. These motions are locked in by gravity and cannot be redirected by individual humans. In practical terms, this distance does not expand human reach. It does not allow contact, landing, or observation from new vantage points. It is motion without agency. This highlights an important idea that will stay with us throughout this discussion. Distance alone is not what makes travel meaningful. Direction, control, and the ability to change your environment matter just as much. From a scientific standpoint, this passive distance is still useful. It reminds us that humans are not stationary creatures trapped on a still planet. We're embedded in a dynamic system, constantly moving through space at speeds far beyond anything we can feel. This helps explain why spaceflight begins with relative motion rather than absolute speed. When a spacecraft launches, it does not start from zero. It already carries Earth's orbital velocity around the Sun. That inherited speed is what allows relatively modest rockets to reach other planets at all. Without it, interplanetary travel would be even harder. But for our central question, how far could a human intentionally travel in one lifetime? Passive motion must now fade into the background. It sets the stage, but it does not define the limits we care about. To go farther in a meaningful way, a human must leave the surface of Earth. And that begins with the simplest but most demanding step of all, reaching orbit. Leaving Earth is not primarily about distance, it is about speed. To remain above the planet without falling back, a spacecraft must move sideways fast enough that as it falls, the ground curves away beneath it. This balance between forward motion and gravity is what we call orbit. Low Earth orbit begins at an altitude of roughly 160 kilometers above the surface. In vertical terms, this is not very far. A commercial airplane cruises at about 10 kilometers. The highest mountain on Earth reaches almost 9 kilometers. Reaching orbit is not about climbing high, it is about accelerating sideways. To stay in low Earth orbit, a spacecraft must travel at about 7.8 kilometers per second, nearly 28,000 kilometers per hour. This is more than 30 times faster than a commercial jet, and thousands of times faster than walking. Achieving this speed is the main challenge of spaceflight. Almost all of the energy used during a rocket launch goes into reaching orbital speed, not altitude. Once that speed is reached, staying in orbit requires very little additional energy. The spacecraft simply continues falling around Earth. For a human, reaching orbit represents a major threshold. Below orbital speed, any jump into space is temporary. Above it, long-term travel becomes possible. This is why low Earth orbit is the gateway to all further exploration. The human body can tolerate the forces involved in reaching orbit, but only briefly. Astronauts experience several times Earth's gravity during launch. This is uncomfortable, but survivable for minutes. Sustaining such acceleration for hours or days would not be possible without serious harm. Once in orbit, however, the physical environment changes dramatically. Gravity still exists, but the constant freefall creates the sensation of weightlessness. This has well-documented effects on the body. Muscles weaken, bones lose density, fluids shift toward the head, vision can change over time. Despite these challenges, humans have lived in low Earth orbit for months at a time. Some astronauts have stayed for nearly a year. This makes orbit the longest duration environment in which humans have actually lived off Earth. From the perspective of distance travelled, orbit is surprisingly powerful. The International Space Station circles Earth about 16 times per day. Each orbit covers roughly 40,000 kilometres. Over one day, that is more than 600,000 kilometres travelled. Over a year, it adds up to over 200 million kilometres. If a human could remain in orbit for decades, assuming perfect health and resupply, the total distance travelled would be enormous. In purely numerical terms, someone living in low Earth orbit for 40 years would travel billions of kilometres. But again, this distance has a familiar limitation. The traveller remains close to Earth. They do not move outward into the solar system. Their path is repetitive and constrained by Earth's gravity. Orbit allows sustained high-speed travel, but it does not allow escape. To go farther, a human must increase speed beyond what orbit requires. That means leaving Earth's gravitational hold entirely. As we move on, we will explore what it takes to go beyond orbit, and how much farther that step actually carries a human within the span of one lifetime. The International Space Station offers the clearest real-world example of sustained human motion through space. It is not experimental in the abstract. It is a working environment where humans live, move, sleep, and age while travelling at orbital speed. This station orbits Earth at approximately 7.66 kilometers per second. That is about 27,600 kilometers per hour. At this speed, it completes one full orbit every 90 minutes. Day and night pass quickly. The sun rises and sets 16 times every 24 hours. This speed is not chosen arbitrarily. It is the precise balance required to stay in orbit at the station's altitude. Any slower, and the station would gradually descend and burn up in the atmosphere. Any faster, and it would move into a higher orbit or escape Earth's gravity entirely. For the astronauts aboard, this speed is constant. Once achieved, it requires only small adjustments to maintain. Engines fire occasionally to counteract atmospheric drag and orbital decay, but most of the time, the station simply coasts. From the standpoint of distance, the numbers are striking. Each orbit covers roughly 40,000 kilometers, similar to Earth's circumference. Over a single day, the station travels about 680,000 kilometers. In 1 week, that becomes nearly 5 million kilometers. In 1 year, over 350 million kilometers. If a human were to live aboard the station for 1 full year, they would travel a distance comparable to more than twice the average distance from Earth to the Sun. Yet they would never be more than a few hundred kilometers above Earth's surface. This illustrates an important principle. Speed alone does not guarantee exploration. High speed can produce large distances without producing separation. The station's motion is locked into Earth's gravitational system. Its velocity is almost entirely sideways relative to the planet. Very little of it contributes to moving away from Earth. As a result, the enormous distance travelled does not bring astronauts closer to the Moon, Mars, or any other destination. From a biological perspective, however, the ISS is critical. It represents the longest sustained exposure of humans to space conditions at high speed. The data gathered there tells us what decades of orbital travel might do to the body. We know that muscle atrophy accelerates in microgravity. Bones lose density at a rate of about 1% per month without countermeasures. Vision changes have been observed due to fluid shifts inside the skull. Sleep cycles are disrupted. The immune system behaves differently. Exercise mitigates many of these effects, but not all. Even with strict routines, astronauts return to Earth physically weaker than when they left. Recovery takes months. Psychologically, the station also reveals limits. Crews live in confined spaces, isolated from Earth, with a small group of people and limited privacy. While astronauts are highly trained and selected, long-duration missions still impose mental strain. All of this matters because orbit represents the most forgiving environment for high-speed human travel. Radiation levels are lower than in deep space. Communication with Earth is nearly instantaneous. Rescue and return are possible. If humans struggle at orbital speeds while remaining close to Earth, that tells us something important about the limits of faster and farther travel. Still, the ISS shows that humans can survive and function while moving through space at nearly 8 kilometers per second for months at a time. That speed is real. It is proven. It is the baseline from which any further human travel must build. In the next step, we will ask a natural question. If orbit allows sustained high speed, what happens if we stay there much longer? How far could a human travel in one lifetime by simply continuing to circle Earth? If we imagine a human spending a very long time in low Earth orbit, the numbers begin to feel almost surreal. This is not because orbit brings us closer to distant destinations, but because speed is maintained continuously, day after day, year after year. Let us consider a hypothetical but grounded scenario. Suppose a human could remain in low Earth orbit for 40 years. This is far longer than any astronaut has stayed, but it is a useful upper bound when exploring limits. At orbital speed, about 7.7 kilometers per second, a person travels roughly 660,000 kilometers per day. Over 1 year, that becomes about 240 million kilometers. Over 40 years, the total distance travelled would exceed 9.5 billion kilometers. That is more than the average distance from the Sun to Pluto. And yet, during all of this motion, the person would never be farther than a few hundred kilometers from Earth's surface. This contrast highlights something essential about space travel. Distance travelled and distance from origin are very different quantities. Orbit maximizes the former while minimizing the latter. From the perspective of human endurance, this scenario quickly reveals its limits. No human has lived continuously in orbit for decades. The longest single mission durations approach 1 year, and even those require extensive medical monitoring. Over decades, cumulative radiation exposure will become severe. Earth's magnetic field offers partial protection in low orbit, but not complete. Damage to DNA would accumulate. Cancer risk would rise significantly. The nervous system could be affected. Bone density loss, even with exercise, would likely reach levels incompatible with normal function. Muscles would weaken. The cardiovascular system would adapt to microgravity in ways that might not be reversible. There is also the issue of resupply. Orbiting Earth for decades would require continuous delivery of food, water, oxygen, spare parts, and medical supplies. The logistical effort would be enormous and likely impractical. So while orbit allows immense distance to accumulate in a lifetime, it does not meaningfully expand how far a human can go in terms of exploration. It is motion without departure. This is why the next step in space travel has always been leaving orbit. The moon landings were not about travelling far in total distance. They were about changing reference frames, breaking free of Earth's immediate gravitational control. Once a spacecraft leaves Earth orbit, its path is no longer a closed loop. Distance from Earth begins to grow in a way that orbit never allows, but this comes at a cost. To leave orbit, speed must increase, and increasing speed, as we have seen, demands energy, fuel, and mass. Each of these brings its own limitations, especially when a human body's involved. As we continue, we will move outward for the first time. We will look at what it takes to escape Earth's gravity entirely, and how much that step truly increases the distance a human can travel within one lifetime. Leaving Earth orbit is the moment when space travel becomes genuinely outward. Up to this point, motion has been fast but contained. Escape changes the geometry of the journey. To leave Earth's gravitational influence, a spacecraft must reach escape velocity. From low Earth orbit, this requires increasing speed from about 7.8 kilometers per second to roughly 11.2 kilometers per second. This additional speed does not lift the spacecraft higher. It allows the spacecraft to break free from a closed orbital path. Reaching escape velocity is demanding. It requires a significant amount of extra energy delivered over a short time. For human missions, this energy must be provided in a way that does not expose the crew to extreme acceleration or vibration. That limits how aggressively engines can fire. Once escape velocity is achieved, something important happens. The spacecraft no longer circles Earth. It begins to move away along an open trajectory. Distance from Earth increases continuously. For the first time, the distance travelled contributes directly to exploration rather than repetition. However, escaping Earth does not mean escaping gravity entirely. The spacecraft remains under the influence of the Sun. In fact, once Earth's pull weakens, the Sun becomes the dominant gravitational force. The spacecraft enters a solar orbit similar to Earth's, but slightly different in speed and shape. This means that leaving Earth orbit does not automatically send a human far into the solar system. It changes the frame of reference from Earth-centered to Sun-centered. Further travel requires additional changes in speed. From a biological perspective, leaving Earth orbit also increases risk. Earth's magnetic field weakens rapidly with altitude. Radiation levels rise. Solar storms become more dangerous. Communication delays increase slightly, though still manageable within the inner solar system. Psychologically, the sense of separation grows. Earth becomes a distant sphere rather than a presence filling half the sky. This change is subtle at first but meaningful. Humans evolved with a constant horizon, familiar landmarks, and immediate environmental feedback. Deep space removes those cues. In terms of distance covered, the initial act of escaping Earth does not add much on its own. The distance from Earth grows slowly at first. What matters is the new freedom of trajectory. The spacecraft is now free to approach other bodies in the solar system. This is why most interplanetary missions involve a sequence: reach low Earth orbit, escape Earth's gravity, and then adjust speed relative to the Sun. Each step builds on the last. None can be skipped. For a human lifetime, leaving Earth orbit is a necessary but not sufficient condition for travelling far. It opens the door, but it does not carry the traveller very far by itself. As we move on, we will look at the technology that has actually carried humans beyond Earth orbit, chemical rockets, and examine what their real limits are when a living person is on board. Every human who has ever left Earth has done so using the same basic technology: chemical rockets. Despite decades of progress in the electronics, materials, and computation, the fundamental method of propulsion has not changed. Chemical energy, released through controlled combustion, produces high-speed exhaust that pushes a spacecraft forward. Chemical rockets are powerful, but they are also limited in ways that directly shape how far a human can travel in one lifetime. The key limitation is energy density. Chemical bonds store only a modest amount of energy per kilogram compared to other possible sources such as nuclear reactions. This means that to achieve high speeds, rockets must burn large quantities of fuel. Most of a rocket's mass at launch is fuel used to accelerate the remaining fuel. This leads to a familiar pattern. Rockets are built in stages. As fuel is burned, empty tanks are discarded to reduce mass. Without staging, reaching orbit would be nearly impossible. Even with staging, the achievable speeds are tightly constrained. For human missions, these constraints are even tighter. The spacecraft must include a pressurized cabin, life support systems, radiation shielding, temperature control, and redundancy for safety. Every added system increases mass. Increased mass requires more fuel. More fuel increases mass again. This cycle limits how much speed can realistically be achieved. Chemical rockets also deliver their energy over short periods. Launch and major burns typically last minutes, not hours or days. After that, the spacecraft coasts. This means that most chemical rocket missions involve brief accelerations followed by long periods of passive travel. This mode of travel is well suited for reaching orbit, the Moon, and nearby planets. It is not well suited for continuous acceleration that would allow much higher cruising speeds. Historically, the fastest crewed spacecraft ever flown was during the Apollo missions. On the return trip from the Moon, astronauts reach speeds of about 11 kilometers per second relative to Earth. That record still stands. At these speeds, humans can move efficiently within the Earth-Moon system and reach Mars over several months. But these speeds are tiny compared to what would be needed for interstellar travel within a lifetime. Another limitation is thermal stress. High-speed travel through space does not generate heat the way atmospheric flight does, but entering or leaving gravitational wells does. Re-entry into Earth's atmosphere from lunar speeds produces extreme heating. Shields must be thick and heavy, further increasing mass. Chemical rockets also impose scheduling constraints. Interplanetary missions must wait for favorable planetary alignments to minimize fuel use. These launch windows occur months or years apart. A human lifetime contains only a limited number of such opportunities. Because of these factors, chemical rockets define a practical boundary. They allow humans to travel millions of kilometers reliably. They allow missions lasting months or, at most, a few years. But they do not allow steady increases in speed over decades. From the perspective of one human lifetime, chemical rockets enable travel across the inner solar system. They do not enable travel to the outer solar system and back, and they certainly do not enable reaching another star. This is not a failure of imagination. It is a consequence of physics. Chemical energy simply does not scale to the distances involved when biology must be protected along the way. As we continue, we will use real destinations, the Moon and Mars, as benchmarks. These are not hypothetical limits. They are places humans have visited or seriously plan to visit, and they provide realistic anchors for how far a human can go in one lifetime using known technology. The Moon is the first and most important benchmark for human travel beyond Earth orbit. It is close enough to reach within days, yet far enough to represent a complete departure from Earth's immediate environment. Everything we know about human deep space travel begins here. The average distance from Earth to the Moon is about 384,000 kilometers. This distance varies slightly because the Moon's orbit is not perfectly circular, but the variation does not change the overall picture. In cosmic terms, the Moon is extremely close. In human terms, it is very far. The Apollo missions took about 3 days to reach the Moon. During that time, astronauts travelled at speeds of roughly 10 to 11 kilometers per second. This was achieved using chemical rockets and carefully planned trajectories. The journey was short enough that life support, radiation exposure, and psychological stress remained manageable. This matters because it shows what is possible within a human lifetime with proven technology. Humans can leave Earth, travel hundreds of thousands of kilometers, land on another world, and return safely, all within a mission lasting less than 2 weeks. From the perspective of distance, a round trip to the Moon adds less than 1 million kilometers to a human's travel. Compared to the billions of kilometers accumulated by orbiting Earth, this is small. But unlike orbital distance, lunar travel represents meaningful displacement. Once a human reaches the Moon, Earth is no longer beneath them, it is far away in the sky. Communication delays become noticeable. Rescue becomes difficult. This psychological shift is as important as the physical one. The Moon also exposes astronauts to deep space conditions. Earth's magnetic field no longer provides protection. Cosmic radiation levels increase. Solar storms become a serious threat. These factors limit how long humans can safely remain beyond Earth orbit. Apollo missions lasted only a few days on the lunar surface. Even proposed future missions involve stays of weeks or months, not years. This reflects real biological constraints. As a benchmark, the Moon shows that humans can travel hundreds of thousands of kilometers intentionally and return. It also shows that such missions consume a significant fraction of acceptable risk and resource budgets. If we ask how far a human could travel in one lifetime by repeating Moon missions, the answer is limited by opportunity rather than distance. A person could fly to the Moon multiple times over a career, accumulating a few million kilometers of meaningful travel. But this does not extend reach much beyond Earth's neighborhood. The Moon is not a stepping stone to the stars, it is a proving ground. It teaches us how difficult it is to leave Earth at all. With the Moon established as our first benchmark, the next natural step outward is Mars. Mars is not just farther away, it introduces time as a much harsher constraint. Mars represents a fundamental shift in human space travel, not because it is dramatically farther than the Moon, but because reaching it forces humans to spend long periods moving through deep space. Time becomes the dominant challenge. The distance from Earth to Mars varies widely. At its closest approach, Mars can be about 56 million kilometers away. At its farthest, more than 400 million kilometers. Human missions are planned around favorable alignments that minimize distance and fuel use. But even under ideal conditions, Mars is never close in the way the Moon is. Using chemical rockets and current mission planning, a one-way trip to Mars typically takes between 6 and 9 months. This is not because spacecraft are slow in an absolute sense, but because trajectories are chosen to conserve fuel rather than minimize time. Faster routes exist in theory, but they require much more energy and expose the crew to greater risks. During this journey, astronauts would be completely outside Earth's protective magnetic field for months. Radiation exposure becomes a constant concern. High-energy particles from the Sun and beyond the solar system pass through spacecraft walls, damaging cells and increasing long-term health risks. Unlike short lunar missions, this exposure cannot be easily limited. Life support systems must function continuously for the entire duration. Food, water, air recycling, waste management and medical care must all operate reliably with no possibility of resupply. Any failure must be repairable with what is already on board. Psychologically, the Mars journey is also demanding. Communication delays range from several minutes to over 20 minutes one way. Conversations with Earth are no longer real-time. The crew must operate with a high degree of autonomy, knowing that help is far away. From the perspective of distance, a Mars mission adds tens or hundreds of millions of kilometers of intentional travel. A round trip, including time spent waiting for planetary alignment to return, could last 2 to 3 years and cover well over 1 billion kilometers in total path length. But here, an important distinction emerges. Much of that distance is not productive movement. Spacecraft often follow long curved trajectories dictated by orbital mechanics. They spend months coasting through empty space, slowly intersecting Mars' orbit at the correct angle and time. For a human lifetime, Mars is significant not because it is the farthest reachable destination, but because it consumes time. A single Mars mission occupies years. Multiple Mars missions would occupy decades. The human body ages while waiting, drifting, and adapting. It is theoretically possible for a human to spend a large portion of their adult life traveling between Earth and Mars. Over 40 years, someone might complete several such journeys. The total distance traveled could be several billion kilometers, yet even this ambitious scenario remains confined to the inner solar system. Mars does not bring humans closer to the outer planets in a meaningful way. Each additional destination increases travel time dramatically. Mars shows us the shape of the problem. Distance alone is not the obstacle. Duration is. The farther we go, the more time is consumed simply getting there, regardless of speed improvements. For a human lifetime, Mars sits near the outer edge of practical exploration. Beyond it, travel times stretch from years into decades, and biological limits begin to dominate every calculation. As we move forward, we'll consider what happens if humans attempt to go farther still, outward toward the outer planets, and why those destinations quickly exceed what one lifetime can reasonably support. Once Mars enters the picture, the inner solar system begins to feel both vast and tightly constrained at the same time. Mercury, Venus, Earth, and Mars are separated by tens to hundreds of millions of kilometers, yet all of them orbit the Sun relatively close together when compared to the full scale of the solar system. In theory, a human could travel between multiple inner planets over the course of a lifetime. With chemical propulsion and careful mission planning, it is possible to move from Earth to Venus, return, then travel to Mars, and perhaps repeat variations of these journeys. Each trip would add significant distance to the total path traveled. However, this theoretical freedom is quickly limited by time. Every interplanetary journey must wait for alignment. Planets move continuously, and efficient travel requires launching when their positions allow a fuel-efficient transfer. These launch windows occur at fixed intervals. For Earth and Mars, optimal windows open roughly every 26 months. Miss one, and you wait over 2 years. This waiting time matters because a human lifetime does not pause between missions. Aging continues whether you're coasting through space, waiting in orbit, or training on Earth. A single Earth-Mars-Earth mission can occupy 2 to 3 years. Add recovery time, preparation and rest, and each mission might consume 4 to 5 years of a person's life. Even under optimistic assumptions, a human could complete only a limited number of such journeys. If we imagine an extreme but physically grounded scenario, a person might spend 30 to 40 years actively engaged in interplanetary travel. Over that time, They might complete several Mars missions and perhaps 1 or 2 missions to Venus. The total distance travelled could reach several billion kilometres, but the inner solar system does not scale smoothly. The farther you go, the longer each mission becomes. Travelling to Jupiter, for example, takes several years one way using chemical propulsion. Saturn takes longer. Uranus and Neptune are measured in decades. This creates a practical boundary. The inner planets are reachable within timescales compatible with a human lifespan. The outer planets are not, at least not with humans on board using known technology. Even within the inner solar system, biological constraints accumulate. Radiation exposure increases with every deep space mission. Muscle and bone loss compound. Psychological fatigue builds. The body does not reset fully between journeys. There is also the question of diminishing returns. Each additional mission adds distance but not access. After visiting Mars once, visiting it again does not expand the frontier. It repeats an already achieved reach. So when we ask how far a human could travel in one lifetime within the inner solar system, the answer depends on how we define far. In terms of total kilometres traced through space, the number can be very large. Billions of kilometres are plausible. In terms of outward reach, how far from Earth a human could go, the answer stabilises near Mars. Venus and Mercury lie closer to the Sun. Mars lies farther out. Beyond that, time becomes the dominant barrier. This leads to an important realisation. Human space travel within one lifetime is not limited by curiosity or bravery. It is limited by how slowly planets move relative to one another and how quickly human bodies age. The inner solar system is the full practical arena for lifetime human travel, using current physics and biology. It is wide enough to feel immense, yet small enough to be bounded by time. As we continue, we will look at a powerful technique that spacecraft use to extend their reach without increasing fuel: gravity assists. These maneuvers reshape trajectories and stretch distance, but they do not escape the limits of a single human life. Gravity assists are one of the most elegant techniques in space travel. They allow a spacecraft to change speed and direction without carrying additional fuel, using the gravity of planets as a kind of moving ramp. When a spacecraft approaches a planet, it falls into the planet's gravitational field. As it swings around the planet and exits, it can steal a small amount of the planet's orbital energy. From the planet's perspective, the loss is negligible. From the spacecraft's perspective, the gain can be substantial. This technique has been used extensively by robotic probes. It is how spacecraft like Voyager, Galileo, and Cassini reached the outer solar system using chemical rockets alone. Without gravity assists, those missions would have required far more fuel or would not have been possible at all. For humans, gravity assists offer both opportunity and limitation. On the positive side, gravity assists can increase speed without increasing onboard fuel mass. This is extremely attractive for human missions, where mass is already constrained by life support needs. In principle, a crewed spacecraft could use gravity assists to reach farther destinations than direct travel would allow. However, gravity assists come with trade-offs. They require very precise timing. The spacecraft must arrive at the right place at the right time to intersect the planet's path. This often results in long, looping trajectories that take years. These extended travel times are acceptable for robotic probes. They are much harder for humans. Every extra year spent coasting through deep space adds radiation exposure, increases psychological strain, and consumes life support resources. Gravity assists also do not provide unlimited speed increases. The amount of energy that can be gained depends on the mass and orbital speed of the planet. Jupiter provides the strongest assists because it is massive and moves quickly around the Sun. Inner planets offer smaller gains. Even with optimal gravity assists, travel to the outer planets takes many years. Voyager 2, for example, used gravity assists to visit Jupiter, Saturn, Uranus, and Neptune. The journey to Neptune took over 12 years, and that was without a human on board. For a human lifetime, gravity assists can stretch reach, but not dramatically. They might reduce fuel requirements or slightly shorten travel time to destinations like Mars or the asteroid belt. They do not make interstellar travel feasible, nor do they make long missions biologically safe. Another subtle limitation is that gravity assists commit the spacecraft to a fixed path. Once the maneuver is planned and executed, changing course requires fuel that may not be available. This reduces flexibility in emergencies. So while gravity assists are a powerful tool, they do not fundamentally change the shape of the problem. They help spacecraft go farther with the same fuel, but they do not reduce the time humans must spend in deep space. In the context of one lifetime, gravity assists allow humans to reach the edges of the inner solar system more efficiently. They might make asteroid missions or extended Mars missions more practical, but they do not move the boundary outward to the stars. As we continue, we will now look at the fastest human-made objects ever built, robotic probes, and use them as an upper benchmark for speed and distance. This comparison will help clarify how far a human could go if we pushed existing technology to its absolute limits. To understand the outer edge of what human technology can achieve, it helps to look at spacecraft that were not designed to carry humans at all. The Voyager probes are our clearest benchmarks. They represent the fastest, farthest travelling objects humanity has ever built. Voyager 1 and Voyager 2 were launched in 1977. They were small, lightweight, and built to survive harsh environments without repair. Most importantly, they did not need air, water, food, or protection for a living body. This freedom allowed them to reach speeds and distances that human missions cannot. After a series of gravity assists, Voyager 1 reached a speed of about 17 kilometers per second relative to the Sun. That is more than twice the speed required for low Earth orbit, and significantly faster than any crewed spacecraft has ever travelled for long durations. At this speed, Voyager 1 covers roughly 540 million kilometers each year. Over decades, that distance accumulates steadily. Today, it is well beyond the outer planets, travelling through interstellar space, far outside the protective bubble of the Sun's influence. This is important because it gives us a realistic upper bound. Voyager's speed was not achieved with exotic physics. It used chemical rockets and gravity assists, technologies we already understand. In principle, a human-rated spacecraft could be accelerated to similar speeds, but in practice, the differences are profound. Voyager carries no shielding against radiation. Its electronics degrade slowly, but it does not suffer biological damage. A human travelling at Voyager speed would be exposed to intense cosmic radiation for decades. Even with heavy shielding, the accumulated dose would likely be fatal long before the journey ended. Voyager also does not care about time. It has no deadline. It can take decades to cross regions that would consume a large fraction of a human life. For a probe, a 40-year journey is simply a design requirement. For a human, it is nearly an entire lifespan. Still, Voyager provides a useful thought experiment. If a human could somehow travel at Voyager-like speed for 40 years, they would cover over 20 billion kilometers. That would take them well beyond Pluto's orbit and deep into the outer reaches of the solar system. But even this astonishing distance falls short of the nearest star by an enormous margin. Proxima Centauri, the closest star beyond the Sun, is over 40 trillion kilometers away. At Voyager speed, reaching it would take more than 70,000 years. So Voyager teaches us two quiet lessons. First, human technology can already send objects very far, very fast, when biology is removed from the equation. Second, even our fastest probes barely begin to cross the gulf between stars. For a human lifetime, Voyager represents a ceiling. It shows how far distance can grow if speed is maximized and time is allowed to run. And it shows how quickly biology becomes the limiting factor when we imagine placing a human inside that machine. In the next step, we will translate Voyager's speed into a human context more directly, asking a precise question. If a person could travel at Voyager-like speed for their entire adult life, how far would they actually get? Let us now translate the Voyager benchmark into human terms as carefully and realistically as possible. This is not a proposal, but a thought experiment grounded in known physics and known biology. Voyager 1 travels at roughly 17 kilometers per second relative to the Sun. This speed is steady. There is no further acceleration. It simply continues forward, year after year, coasting through space. At that speed, the spacecraft covers about 540 million kilometers per year. If we imagine a human travelling continuously at this speed for 40 years, an optimistic estimate for the maximum span of active adult travel, the total distance would be around 21.6 billion kilometers. That distance is enormous by human standards. It is far beyond the orbit of Pluto. It carries the traveller deep into the outer solar system, past the Kuiper belt, and toward the boundary where the Sun's influence fades into interstellar space. But it is essential to slow down here and notice something subtle. Despite travelling for decades at the fastest sustained speed ever achieved by a human-made object, the traveller would still be inside the galaxy's smallest neighbourhoods. They would not be close to another star. They would not be close to anything familiar at all. The nearest star system is more than 40 trillion kilometers away. 21 billion kilometers is less than 0.1% of that distance. Even at Voyager speed, space remains overwhelmingly large. Now consider the biological side of this scenario. A human travelling at Voyager speed would spend decades outside Earth's magnetic field. Radiation exposure would be constant and intense. Even with heavy shielding, high-energy cosmic rays would penetrate tissues and damage DNA. Current models suggest that fatal cancer risk would become very high long before 40 years had passed. Psychological stress would also accumulate. Decades of isolation, confinement, and sensory monotony would challenge even the most resilient minds. Communication with Earth would become slower and slower, eventually stretching to hours, then days. Real-time contact would vanish. There is also the problem of supplies. A human cannot coast indefinitely without maintenance. Food systems fail, machines degrade, micrometeoroid impacts accumulate. A spacecraft designed to support a human for decades would need to be extraordinarily massive and complex, which would make achieving Voyager-like speed even harder. So while Voyager speed provides a numerical upper bound, it is not a practical one for humans. It tells us what distance looks like when time is used efficiently, but it does not tell us what survival looks like. This comparison reveals an important truth. Speed alone does not make deep space accessible to humans. Time and biology dominate the equation long before speed reaches its theoretical limits. In a single human lifetime, even travelling at the fastest speeds we have ever achieved, a person would remain bound to the Sun's neighbourhood. the stars would still be unreachable, not because of lack of technology, but because the distances are simply too large for biological life moving at sublight speeds. Voyager's journey is quiet and patient. It does not hurry. It does not need to arrive. Humans, by contrast, live inside a narrow window of time. Our journeys must fit inside that window, or they end unfinished. As we move forward, we will now approach the boundary where many discussions turn abstract, the edge of the solar system itself. We will look at what it means to reach that boundary, and whether doing so within a human lifetime changes what is possible. When people imagine the edge of the solar system, they often picture a clear boundary, a line where the sun's domain ends and interstellar space begins. In reality, this boundary is gradual and defined by invisible forces rather than physical markers. The most commonly used boundary is the heliopause. This is the region where the solar wind, a continuous stream of charged particles flowing outward from the sun, slows down and is finally stopped by the pressure of interstellar space. Beyond this point, the influence of the sun fades, and the environment becomes dominated by the galaxy itself. Voyager 1 crossed the heliopause in 2012, about 35 years after launch. At that time, it was roughly 18 billion kilometers from the sun. This distance gives us a concrete reference. It represents the farthest any human-made object has traveled while still functioning and communicating. For a human lifetime, this distance is critical. It shows that even at very high speeds, reaching the true outskirts of the solar system takes decades, not months, not years, decades. If a human were travelling at Voyager-like speed, reaching the heliopause might be possible within 30 to 40 years. On paper, this fits within a lifetime. But the cost of doing so would be extreme. Radiation levels beyond the heliosphere are higher and more constant. The solar wind normally deflects some cosmic radiation. Beyond its reach, a spacecraft is exposed to particles that have travelled across the galaxy for millions of years. These particles are highly energetic and difficult to shield against. Temperature also becomes less forgiving. While deep space is cold, maintaining stable internal temperatures over decades requires continuous energy and functioning systems. Any failure becomes increasingly dangerous as distance from the sun grows and solar power weakens. Communication delays become substantial. At the heliopause, radio signals take more than 17 hours to reach Earth one way. Conversations become impossible. Instructions arrive long after conditions have changed. Psychologically, this matters. Humans rely on feedback, reassurance, and social contact. As distance grows, communication turns from dialogue into delayed messaging. This changes how humans experience connection and support. There is also the issue of return. Reaching the edge of the solar system within one lifetime leaves no time to come back. Any journey that extends this far becomes one way by necessity. A return trip would require another multi-decade span that biology does not allow. So while the edge of the solar system is technically reachable within a human lifetime at extreme speeds, it represents the outermost limit of plausible human travel using known physics. It is not a practical destination. It is a boundary that marks the end of what one life can contain. Reaching it would not open new worlds. It would not bring humans closer to the stars in any meaningful way. It would simply mark the point where the sun's influence fades into the broader galaxy. This realization prepares us for the next step in our exploration, understanding just how far away the nearest star really is, and why that distance reshapes every discussion about human travel. The nearest star beyond our Sun is Proxima Centauri, part of a small star system just over 4 light-years away. In everyday terms, This distance is almost impossible to picture. Light itself, the fastest thing in the universe, takes more than 4 years to cross it. In kilometers, the distance is about 40 trillion. This number matters because it reveals a sharp boundary between solar system travel and interstellar travel. Everything we have discussed so far, Earth orbit, the Moon, Mars, even the heliopause, fits inside a scale of billions of kilometers. The nearest star is tens of trillions of kilometers away. This is not a small step outward, it is a jump of more than 1,000 times. At Voyager 1 speed of about 17 kilometers per second, reaching Proxima Centauri would take roughly 75,000 years. That is not an exaggeration or a rounded figure, it is the direct result of dividing distance by speed. No improvement in human endurance, medicine, or psychology changes this number in a meaningful way. Even if humans lived for several centuries, the journey would remain impossibly long. One might imagine increasing speed dramatically, but here the constraints tighten quickly. As speed increases, energy requirements rise steeply. Shielding against radiation and collisions becomes harder. Time dilation effects begin to appear, but only at speeds close to that of light. For humans, travelling even 1% of the speed of light would be revolutionary. At that speed, reaching Proxima Centauri would take about 400 years from Earth's perspective. That is still far beyond one lifetime. At 10% of the speed of light, the journey would take around 40 years, roughly one human lifetime. But achieving that speed introduces problems that are not merely technical, they are physical. The energy required to accelerate a human-sized spacecraft to such speeds is immense, far beyond what chemical rockets or even near-term nuclear systems can provide. The spacecraft would collide with interstellar dust at enormous energies, releasing radiation inside the hull. Shielding would need to be extraordinarily thick and massive. Even if these challenges were solved, deceleration becomes another problem. Reaching another star is not useful unless you can slow down. Slowing down from relativistic speeds requires just as much energy as speeding up. So the distance to the nearest star defines a hard boundary. Within one human lifetime, using any technology we can realistically imagine without new physics, interstellar travel is not possible. This is not a failure of ambition, it is a statement about scale. The universe is built with distances that do not align with biological lifespans. As we move forward, we will briefly touch on concepts that often appear at this point in the discussion, light speed and relativity, and explain gently why they do not rescue the human traveller within one lifetime. When distances become as large as the gap between stars, it is natural to reach for light speed as a point of comparison. Light is the fastest thing we know. Nothing with mass can reach or exceed it. In space travel discussions, light speed often appears as a kind of ultimate solution, a number that, if approached, would seem to dissolve distance itself. Light travels at about 300,000 kilometers per second. At that speed, crossing the distance to Proxima Centauri takes a little over 4 years. This fact alone shows why light speed becomes so tempting in human imagination. 4 years is a meaningful amount of time. It fits within a human life. It even fits within a single mission. But light speed is not a target. It is a boundary. According to our best-tested physical theories, anything with mass requires infinite energy to reach the speed of light. Humans, spacecraft, and even individual atoms have mass. That makes light speed unreachable, not just difficult. Still, it is useful as a reference. It tells us how far away things truly are, stripped of human assumptions. When we say a star is 4 light-years away, we are saying that even the fastest possible signal takes years to arrive. Any slower traveller will take longer, much longer. This reference also reveals how slow human travel really is. Voyager's speed, impressive by engineering standards, is about 0.6% of the speed of light. Even if we improved that speed by a factor of 10, or even 100, we would still be far from relativistic travel. At 10 times Voyager speed, reaching the nearest star would take thousands of years. At 100 times Voyager speed, hundreds of years. These are dramatic improvements that still fail to fit inside a human lifetime. Light speed also introduces another subtle point: communication. Even if humans never travel to the stars, we already interact with them through light. When you look at a star, you are seeing it as it was years, decades, or thousands of years ago. Information travels faster than bodies ever can. In this sense, humans already reach the stars through observation. Telescopes extend vision across light years and even across cosmic time. This is not travel in the physical sense, but it is contact of a kind, a quiet one-way connection. For the human traveller, light speed reminds us that the universe is not scaled to our bodies. The distances between stars are not gaps left for civilizations to cross easily. They are fundamental features of how matter distributed itself after the universe began. Using light speed as a reference helps ground expectations. It shows that the question, how far could a human travel in one lifetime, has a clear answer when framed physically. The answer lies far short of the stars. Within one lifetime, humans can meaningfully travel within the inner solar system, with extreme assumptions, perhaps to its outer edge. Beyond that, distance grows faster than time allows. This is not a limitation unique to our era. It would remain true even if propulsion technology improved by its orders of magnitude, unless the nature of physics itself turned out to be different from what we currently understand. In the next part, we will gently introduce relativity, not as an escape, but as a framework that clarifies why time itself does not bend enough to save the human traveller from cosmic scale. When discussions of long-distance space travel reach their limits, relativity often appears as a possible way forward. The idea is subtle, but tempting. If time can slow down for a fast-moving traveller, perhaps a human could cross great distances within a single lifetime, at least from their own perspective. This idea is rooted in real physics. According to Einstein's theory of special relativity, time does pass more slowly for objects moving at very high speeds relative to a stationary observer. This effect, known as time dilation, has been measured and confirmed many times. Atomic clocks flown on fast-moving aircraft tick slightly slower than identical clocks on the ground. Particles moving near light speed decay more slowly than expected. So the effect is real. However, its usefulness for human space travel is often misunderstood. Time dilation becomes noticeable only at speeds close to the speed of light. At everyday speeds, even at orbital speeds, the effect is so small that it can be ignored. Astronauts aboard the International Space Station age a tiny fraction of a second less than people on Earth over the course of a mission. This difference is measurable but biologically meaningless. To experience significant time dilation, a traveller would need to move at a substantial fraction of light speed. At 10% of light speed, time dilation is still modest. The traveller's clock would run only slightly slower than Earth's. The journey to the nearest star would still take decades for the traveller, and longer for those left behind. At speeds above 50% of light speed, time dilation becomes more dramatic. A journey that takes decades from Earth's perspective might take only years for the traveller. At 90% of light speed, the effect is stronger still. But this is where physics and biology converge to close the door. Reaching such speeds requires enormous energy. The closer you approach light speed, the more energy is required for each additional increase in velocity. This energy grows without bound. Even accelerating a small spacecraft to these speeds would demand resources far beyond anything we can currently imagine producing or storing. There are also severe physical consequences. At relativistic speeds, even sparse interstellar dust becomes dangerous. Collisions with tiny particles would release energy equivalent to high-energy radiation passing through the spacecraft. Shielding against this would need to be extremely thick, increasing mass and making acceleration even harder. Deceleration presents the same problem in reverse. Slowing down from relativistic speed requires just as much energy as speeding up. Without a way to decelerate, a traveller would simply pass through a star system at extreme speed, unable to stop or explore. Most importantly, time dilation does not extend biological tolerance. From the traveller's point of view, they are still aging normally. Their cells still accumulate damage, radiation exposure still harms tissue, psychological strain still accumulates. Time dilation does not make the body more durable. It only changes how much external time passes while the body ages. So relativity does not offer a loophole. It clarifies the limits rather than dissolving them. In a sense, relativity tells us something quietly humbling. The universe allows extreme travel only at the cost of extreme conditions. The physics that permit time to slow down also make those speeds hostile to life. For a human lifetime, relativity confirms what simpler calculations already suggest. Without new physics, not new engineering but new physical laws, the distances between stars remain far beyond what a single life can cross. This does not diminish the importance of relativity. It deepens our understanding of why the universe feels so large and why human experience occupies such a narrow slice of it. As we move on, we will step back from speed and time and return to something closer to the body itself. We will look at the biological constraints that quietly shape every realistic journey, no matter how advanced the technology becomes. At this point, it becomes clear why relativity, while fascinating and real, does not change the practical limits of how far a human can travel in one lifetime. The reason is not a single obstacle, but the way many small constraints stack together. First, consider energy. Relativistic travel demands extraordinary amounts of it. Even reaching a small fraction of the speed of light requires energy far beyond what chemical or nuclear systems can deliver in a compact, controllable form. For a human-rated spacecraft, this energy would need to be generated, stored, and released safely. Each of those steps introduces mass, complexity, and risk. Second, consider acceleration. Humans cannot tolerate continuous high acceleration. To reach relativistic speeds gently enough for the body, acceleration would need to be spread over months or years. During that entire time, the spacecraft would be consuming energy and exposing the crew to deep space conditions. The journey would already be long before the destination came into view. Third, consider shielding. At high speed, space is no longer empty. Hydrogen atoms, dust grains, and stray particles become a constant stream of high-energy impacts. These impacts generate radiation inside the spacecraft. Shielding against this radiation adds mass, which makes reaching high speed even harder. There is no simple balance point where shielding becomes easy. Fourth, consider deceleration. Any journey that does not include a safe way to slow down is not a journey in the human sense. Arriving at a star system at near light speed without the ability to stop is equivalent to never arriving at all. Deceleration requires the same magnitude of energy as acceleration, doubling the problem. And finally, consider biology. Even if all of the engineering challenges were solved, the human body would still age at its normal rate from its own perspective. Cells would still divide. DNA would still accumulate damage. Organs would still wear down. Time dilation does not slow biological aging from the inside. So relativity changes how journeys are measured, but it does not change how they are lived. This is why discussions of human space, travel within one lifetime, always return to the same conclusion. Without rewriting the laws of physics, human travel is confined to distances that can be crossed at modest fractions of light speed. Under conditions that biology can tolerate, those distances lie within the solar system. Relativity does not fail us. It simply tells the truth about scale. It tells us that the universe is not built for fast crossing by fragile organisms. It tells us that vast distances are not meant to be bridged casually. And it tells us that human presence in space will always be shaped by the body as much as by machines. With this understanding in place, we can now turn fully toward the human organism itself. We will examine the limits imposed not by engines or equations, but by tissue, cells, and systems that evolved under Earth's sky. No matter how powerful our machines become, every human journey through space must carry a living body along with it. That body brings remarkable adaptability, but it also brings limits that cannot be engineered away. Human biology evolved under very specific conditions: one gravity, a thick atmosphere, a steady magnetic field, a constant supply of food, water, and microbial balance. Space removes or alters all of these at once. One of the most immediate constraints is gravity. In microgravity, the body no longer needs to support its own weight. Muscles weaken quickly. Bones lose calcium and become fragile. Even with daily exercise, astronauts lose bone density at a rate far faster than aging on Earth. Over years, this loss may become irreversible. The cardiovascular system also adapts in ways that are not always helpful. Blood and other fluids shift toward the head. The heart does less work. When returning to gravity, astronauts often experience dizziness, weakness, and difficulty standing. Over very long missions, it is unclear whether the body could fully readapt. Radiation is another constant pressure. On Earth, the atmosphere and magnetic field block most harmful radiation. In deep space, high-energy particles pass through the body, damaging DNA. This damage accumulates silently. It increases cancer risk and may affect the nervous system in ways we do not yet fully understand. Unlike short missions, long journeys do not allow exposure to remain low. Radiation dose grows steadily with time. Shielding helps, but shielding adds mass, and even thick shields cannot stop the most energetic particles. Then there is the immune system. Studies show that immune responses change in space. Some cells become less effective, others become overactive. Latent viruses can reactivate. Over years, these changes could make humans more vulnerable to infection or inflammation. Sleep and circadian rhythms also suffer. Without a natural day-night cycle, the brain struggles to regulate rest. Chronic sleep disruption affects mood, cognition, and physical health. Over decades, this alone could shorten functional lifespan. All of these factors interact. Muscle loss affects mobility, radiation affects healing, sleep disruption affects immunity. Space does not apply one stress at a time. It applies many at once, continuously. This is why time matters so much. The human body can tolerate extreme conditions briefly. It cannot tolerate moderate harm indefinitely. Even small daily stresses accumulate when exposure lasts years or decades. So when we ask how far a human can travel in one lifetime, biology quietly answers before physics does. The body sets a soft but firm boundary. Beyond a certain duration, survival turns into decline. Technology can slow this decline. Exercise, shielding, medicine, and careful design all help. But none remove the underlying truth. Humans are not built for endless exposure to space. As we move on, we will look not at the body alone, but at the systems that must support it: food, air, water, and energy, and how they further constrain long journeys within a single life. Keeping a human alive in space is not a matter of a single machine. It is the coordination of many systems, all of which must function continuously, reliably, and without access to resupply for long periods of time. On Earth, life support is everywhere and invisible. Air circulates freely, water cycles naturally, food is produced by vast ecosystems. In space, every one of these processes must be recreated inside a closed environment. Air is the first requirement. Humans consume oxygen and produce carbon dioxide with every breath. On spacecraft, oxygen must be generated or stored, and carbon dioxide must be removed. Current systems can recycle air effectively, but they rely on filters, chemical reactions, and mechanical components that wear out over time. Water is equally critical. Humans need it not only for drinking, but for food preparation, hygiene, and temperature regulation. Modern spacecraft recycle water from breath, sweat, and waste with high efficiency, but not perfectly. Small losses add up over months and years. Any long-duration mission must carry reserves or rely on systems that have never been tested over decades. Food presents a different challenge. Stored food degrades, nutrients break down, variety becomes limited. Growing food in space is possible, but it requires light, water, nutrients, and careful control of microbial growth. These systems add complexity and mass, and they introduce new failure points. Energy ties all of this together. Life support systems require constant power. Pumps, sensors, heaters, and processors must run continuously. Solar power works well near Earth, but weakens as distance from the Sun increases. Nuclear power offers longer endurance, but introduces safety and engineering challenges, especially for human crews. Closed systems are fragile in a specific way. On Earth, if one component fails, the environment often compensates. In space, failures cascade. A malfunction in air recycling increases carbon dioxide. That affects cognition and sleep. Poor sleep affects maintenance and decision-making. Small errors compound. Time amplifies this fragility. A system designed to work for 6 months may perform well. A system designed to work for 10 years must survive wear, radiation damage, micrometeoroid impacts, and human use without external support. For a human lifetime, this is a defining constraint. Even if propulsion were not a problem, life support would be. Every extra year of travel increases the probability that something critical will fail. This is why long-duration human missions are planned cautiously. Redundancy is added, but redundancy adds mass. Mass reduces speed. Reduced speed increases time. Time increases stress on life support systems. The loop tightens. In theory, a perfectly closed, perfectly stable life support system could support a human for decades. In practice, such systems remain experimental. Earth itself is the only closed life support system we know that works reliably over long timescales. So when we ask how far a human can travel in one lifetime, we're also asking how long a small artificial Earth can remain stable. So far, the answer has been measured in months and years, not decades. As we continue, we will move from physical systems to the human mind. Long before life support systems fail, psychological limits begin to shape what kinds of journeys are truly possible. Long before engines fail or supplies run low, the human mind begins to register distance in a different way. Space travel is not only a physical journey, it is an extended psychological condition shaped by isolation, confinement, and separation from familiar human environments. Humans are deeply social organisms. Our brains evolved in constant interaction with others, with varied landscapes, changing weather, and rich sensory input. Space removes almost all of this. The environment becomes small, repetitive, and artificial. The view rarely changes. Sounds are mechanical. Smells are recycled. Even on the International Space Station, where Earth fills the windows and communication is nearly instant, astronauts report psychological strain. Sleep disturbances, irritability, reduced concentration, and emotional flattening are common. These effects are managed with careful crew selection, structured schedules, and regular contact with Earth. As distance increases, these supports weaken. On a mission to Mars, communication delays stretch from minutes to tens of minutes. Conversations become asynchronous. Questions cannot be answered quickly. Emotional support arrives late. Misunderstandings linger longer. The sense of being truly alone grows. Isolation also changes how time is experienced. Without natural day-night cycles, seasons, or social milestones, days begin to blend together. Weeks lose texture. Months feel abstract. This can reduce motivation and impair long-term planning. Confinement adds another layer. Living in a small space with the same few people for years places constant pressure on relationships. Minor conflicts have nowhere to dissipate. Privacy is limited. There is no opportunity to step away into a larger world. Psychological studies of isolated environments on Earth, polar stations, submarines, remote research bases, show similar patterns. Even with training and voluntary participation, extended isolation leads to increased stress, altered emotional responses, and changes in group dynamics. These environments, however, still allow eventual return. Space travel does not always offer that reassurance. On long missions, especially one-way journeys, the knowledge that Earth is receding and return may not be possible adds a quiet weight to every day. The mind also responds to risk. In space, danger is ever present, but often invisible. A small leak, a radiation spike, a system malfunction. Any of these could be fatal. Living with continuous low-level risk changes how the brain allocates attention and stress hormones. Over years, this can wear down resilience. Importantly, psychological limits are not weaknesses. They are signals. They tell us how human cognition is tuned. Just as bones signal strain under load, the mind signals strain under isolation. For journeys lasting months, humans adapt. For journeys lasting years, adaptation becomes more fragile. For journeys lasting decades, we have no evidence that adaptation is possible at all. This matters deeply when considering how far a human can travel in one lifetime. Even if propulsion and life support could sustain the body, the mind may not remain healthy over such durations in deep space. So distance is not only measured in kilometers, it is measured in how long a human can remain mentally whole while separated from Earth, from society, and from the rhythms that shape the human brain. As we move forward, We will examine proposals that attempt to bypass these limits by changing what we mean by a human traveller, shifting from individuals to generations, and seeing how that changes the question entirely. When journeys become too long for a single human life, one idea appears again and again: the generation ship. Instead of asking how far one person can travel, this concept asks how far a community can travel across multiple generations. A generation ship is designed to operate for centuries or even thousands of years. Children are born on board, grow up in space, and eventually die there, while the ship continues its slow journey. The original travelers never reach the destination; their descendants do. From an engineering perspective, this changes many constraints. Speed can be much lower, because time is no longer limited to one lifespan. Life support systems must be far more stable, but they do not need to protect the same individuals for decades. Instead, they must support a self-sustaining population. From a biological perspective, however, this is no longer the same question. A generation ship does not extend how far a human can travel in one lifetime. It replaces the individual with a lineage. Each person aboard still lives and dies within a normal human span. No single human experiences the full journey. This distinction matters because our original question is personal, not civilizational. It asks about the limits of one life moving through space, not about humanity as an abstract whole. There are also deep psychological and ethical questions. People born on a generation ship did not choose the journey. Their entire world is artificial. Concepts like arrival become myths rather than experiences. Identity becomes tied to maintenance rather than exploration. From a scientific standpoint, generation ships are possible only if many unsolved problems are addressed. Closed ecosystems would need to function without collapse for centuries. Genetic diversity would need to be managed. Social stability would need to persist without external reference points. Even if all of that were solved, generation ships do not answer how far one human can go. They answer how far human culture might propagate over time. So generation ships mark a conceptual boundary. They show that interstellar travel may be possible for humanity as a species, but not as an experience lived by a single person from beginning to end. This reinforces the central theme of our exploration. Distance in the universe is not matched to the scale of individual lives. Some journeys belong to civilizations, not to people. As we continue, we will return to the individual human body and examine other ideas proposed to stretch a lifetime, such as suspended animation, and why these remain uncertain. When the limits of time and biology become clear, another idea often enters the conversation: suspended animation. If a human could sleep through most of a journey, aging slowly or not at all, perhaps distance would no longer be constrained by a single lifetime. In science fiction, this idea is usually presented as cryogenic sleep, a state in which the body is cooled to extremely low temperatures, biological processes nearly stop, and the traveller awakens decades or centuries later, unchanged. In reality, this remains speculative. At present, humans cannot be placed into long-term suspended animation and revived safely. Cooling the body slows metabolism, but it also disrupts cellular processes. Ice crystals form inside cells, damaging membranes and structures. Organs respond differently to cooling, making uniform preservation extremely difficult. Short-term medical hypothermia is used in specific cases on Earth, such as during certain surgeries or after cardiac arrest. In these cases, the body is cooled only slightly and only for hours, not years. Even then, risks are significant and careful monitoring is required. Extending this state to decades introduces problems that are not yet solved. Cells rely on constant repair. DNA damage occurs even at low metabolic rates. Proteins degrade. Without active maintenance, biological systems slowly drift toward failure. There is also the challenge of revival. Restarting a complex, interconnected system like the human body after long dormancy is not simply a matter of warming it up. Chemical gradients must be restored. Neural activity must resume coherently. The immune system must re-engage without attacking damaged tissue. Even if suspended animation were possible, it would not eliminate all constraints. The spacecraft would still need to function for decades. Life support systems would still need power. Radiation would still affect tissues, even at low metabolic rates. Structural failures would still accumulate. Psychologically, suspended animation changes the experience of travel, but it does not eliminate its risks. A traveller who sleeps through most of a journey would awaken in a radically different environment, separated from their original context by decades. Adaptation would still be required. From the perspective of our question, suspended animation also raises a subtle point. If a human spends most of a journey unconscious, is the distance truly experienced within one lifetime? Chronologically, yes. Experientially, no. The body may age less, but the lived experience of time would be compressed into brief waking intervals. The journey would not be a continuous human experience. It would be a series of awakenings separated by absence. This does not make the idea invalid, but it reframes it. Suspended animation does not extend how far a human can actively travel in one lifetime. It changes how that lifetime is spent. For now, suspended animation remains an open research topic, not a tool we can rely on. It may one day allow longer missions within the solar system. It does not currently provide a pathway to interstellar travel within one human life. So once again, the boundary holds. Distance grows faster than biology allows time to stretch. Even ideas that pause aging do not erase the scale of space. As we move forward, we will now look at alternative propulsion concepts, ideas that promise higher speeds than chemical rockets, and ask a careful question. Do any of them meaningfully change the lifetime limit for human travel? When chemical rockets reach their limits, attention naturally turns to other propulsion ideas. These concepts are often described as advanced, but it is important to approach them calmly, without assuming they solve the lifetime problem by default. One alternative is ion propulsion. Ion engines use electricity to accelerate charged particles to very high speeds. They're extremely efficient in terms of fuel use. Spacecraft using ion drives can run their engines for months or years, slowly building up speed. This sounds promising, but the trade-off is thrust. Ion engines produce very little force. They're excellent for robotic probes, which do not mind accelerating gently for long periods. For human missions, low thrust creates problems. The spacecraft must remain in deep space for extended durations while accelerating, increasing radiation exposure and life support demands. Another idea is nuclear thermal propulsion. In this approach, a nuclear reactor heats a propellant, which is then expelled to produce thrust. This can provide higher efficiency than chemical rockets and greater thrust than ion engines. It could shorten travel times to Mars and make some missions more flexible. However, even nuclear thermal rockets do not increase speed by orders of magnitude. They improve margins within the solar system. They do not make interstellar travel feasible within one lifetime. There are also concepts like nuclear electric propulsion, solar sails, and beamed propulsion. Solar sails use pressure from sunlight to slowly accelerate a spacecraft without fuel. Beamed propulsion imagines powerful lasers pushing a sail from afar. These ideas are exciting and some are actively researched, but again they favour small, lightweight probes. Scaling them up to carry humans introduces mass, shielding, and safety challenges that quickly erase their advantages. Perhaps the most important point is this: propulsion concepts tend to trade time for efficiency, or efficiency for complexity. None remove the need to spend long periods in space if distances are large. None eliminate the biological costs of those periods. Even if a propulsion system could double or triple typical spacecraft speeds, the improvement would not change the overall conclusion. A Mars trip might take 3 months instead of 6. A journey to the outer planets might take a decade instead of 2. Interstellar distances would remain out of reach, so advanced propulsion refines what is possible within the solar system. It does not redefine the scale of human travel in one lifetime. This perspective is not pessimistic, it is clarifying. It tells us where engineering effort produces meaningful returns and where it does not. As we approach the end of our core exploration, we will now gather these ideas together and ask a final, grounded question. Given everything we know, how much does advanced propulsion actually change the distance a human can cover in one life? When all advanced propulsion concepts are placed side by side, a clear pattern emerges. They change details, not fundamentals. They reshape routes, shorten some timelines, and expand margins of safety. But they do not rewrite the scale of space relative to a human life. Ion drives, nuclear propulsion, and solar sails can increase efficiency. They allow spacecraft to use less fuel, to adjust trajectories more flexibly, and to reach certain destinations with lower energy cost. For robotic missions, this is transformative. For human missions, it is incremental. Consider Mars again. With chemical rockets, a journey might take 6 to 9 months. With more advanced propulsion, it might be shortened to 3 or 4 months. That matters. It reduces radiation exposure. It reduces time in isolation. It lowers risk. But it does not change the category of the journey. Mars remains a mission measured in years, not weeks. It still occupies a significant portion of an adult life, when preparation, travel, surface stay, and return are included. Now consider the outer planets. Even optimistic projections for advanced propulsion place travel times in the range of many years. Jupiter might be reached in a few years instead of 5 or 6. Saturn in under a decade instead of longer. These are improvements, but they remain incompatible with repeated travel within one lifetime, and for interstellar distances the picture barely changes at all. Increasing speed by a factor of 2 or even 10 does not bridge a gap that is thousands of times larger. The nearest star remains far beyond reach. This leads to a simple but important conclusion. Advanced propulsion stretches the inner solar system. It does not open the stars. For a human lifetime, the practical boundary remains where it has been throughout this exploration. Humans can travel intentionally within the inner solar system, with extreme assumptions, perhaps to its outer edge. Beyond that, time and biology close the door. This does not mean that advanced propulsion is unimportant. It improves safety, it increases reliability, it expands scientific reach, it makes human presence beyond Earth more sustainable. But it does not change the answer to our central question. How far could a human travel through space in one lifetime? The answer is not defined by engines alone. It is defined by the quiet alignment of speed, time, biology, and scale. Technology can bend that alignment slightly, it cannot break it. With this understanding in place, we now widen the lens. We move from engineering limits to natural context, comparing human travel to movement patterns found elsewhere in life on Earth, and seeing what that comparison reveals about scale and adaptation. To better understand the scale of human space travel, it helps to step away from machines and look instead at movement in nature. On Earth, many animals are extraordinary travelers. Their migrations are shaped by evolution, energy limits, and survival needs. The same forces that quietly shape human journeys through space. Consider migratory birds. Some species travel tens of thousands of kilometers each year, flying between breeding and feeding grounds with remarkable precision. Over a lifetime, a single bird may circle the planet multiple times in cumulative distance. This is possible because their bodies evolved specifically for sustained motion, efficient energy use, and environmental navigation. Whales migrate across entire oceans. Monarch butterflies travel thousands of kilometers over multiple generations. Even small insects can traverse continents when conditions allow. These journeys are impressive not because of raw distance, but because they are repeated, purposeful, and biologically supported. Now compare this to human space travel. Humans are not built for long-distance travel in hostile environments without support. When we migrate on Earth, we do so with food, shelter, and social structures. When animals migrate, the environment itself supports them. Air provides lift, water provides buoyancy, ecosystems replenish energy along the way. Space provides none of these. Every kilometer a human travels through space must be engineered. There are no rest stops, no natural replenishment, no environmental assistance. Movement does not emerge from biology. It is imposed by technology. This comparison reveals something subtle but important. Animal migrations succeed because they align with natural systems. They work with gravity, climate, and ecology. Human space travel works against the environment at every step. Gravity must be overcome. Radiation must be blocked. Temperature must be controlled. On Earth, migration distance is often limited not by lifespan, but by energy balance. Animals stop when food runs out or conditions change. In space, humans stop when time, biology, or technology runs out. This helps explain why even the most advanced human journeys feel short compared to cosmic distances. Our movement is not supported by the environment we move through, it is buffered against it. In this light, it becomes clear that space travel is not a natural extension of human migration. It is a fundamentally different category of movement. It is closer to deep sea exploration than to overland travel, but even the deep sea still provides pressure, equilibrium, and chemical stability that space does not. So when we ask how far a human can travel within one lifetime, we're asking how far a fragile, self-contained ecosystem can be carried through an environment that offers nothing in return. This comparison does not diminish human achievement, it clarifies it. Every kilometer traveled in space represents not adaptation, but resistance. Resistance to vacuum, radiation, isolation, and time. As we continue, we will look at how evolution itself shaped human limits, and why our bodies, so capable on Earth, become restrictive when removed from the conditions that formed them. Human limits in space are not accidents. They are the result of millions of years of evolution under very specific conditions. Understanding this helps explain why distance becomes such a powerful barrier once we leave Earth. Human bodies evolved in one gravity, under one atmosphere, protected by a magnetic field and supported by complex ecosystems. bones grew dense enough to support weight, not to float indefinitely. Muscles evolved for walking and lifting, not for resisting long-term atrophy in microgravity. Our balance system depends on gravity as a reference. Remove it, and the brain struggles to interpret motion and orientation. Our cells also evolved under Earth's radiation environment. DNA repair mechanisms are tuned to the background levels of radiation found at the surface of the planet. In deep space, radiation levels are much higher and more energetic. The damage exceeds what these systems are optimized to handle continuously. Even our senses reflect Earth's conditions. Eyes evolved for sunlight filtered by atmosphere. Ears evolved for sound travelling through air. Skin evolved to regulate temperature within a narrow range. Space removes or distorts these inputs, forcing the nervous system into constant adjustment. Evolution works by optimization, not generalization. It does not prepare organisms for every possible environment. It prepares them for the one they reliably inhabit. Humans are extraordinarily well adapted to Earth. That very specialization makes us fragile elsewhere. This is why space travel requires so much technological mediation. Every function that Earth provides automatically must be recreated artificially. Gravity becomes exercise routines and mechanical loading. Atmosphere becomes sealed cabins. Day and night become scheduled lighting. Food becomes stored systems and controlled growth. Each layer of mediation increases complexity. Complexity increases points of failure. Over long periods, failures become more likely, not less. From an evolutionary perspective, this means that long-duration space travel pushes humans outside their adaptive envelope. Short missions are tolerable. Medium missions are stressful but survivable. Very long missions exceed what natural selection prepared us for. This does not mean humans cannot adapt at all. The body shows remarkable short-term plasticity, but plasticity has limits. Adaptation trades one function for another. Bone loss conserves energy but weakens structure. Fluid shifts reduce cardiovascular load but impair vision. These are not neutral changes. So when we ask how far a human can travel in one lifetime, evolution quietly answers alongside physics. It says that humans can function for limited times in extreme environments, but not indefinitely. It says that bodies are not interchangeable with machines. This perspective helps reframe expectations. The goal of human space travel is not to cross the universe, but to carefully extend presence just beyond Earth, within ranges biology can tolerate. As we widen the lens further, we will now consider time itself, not just as a biological limit, but as a natural scale that places human lives within a much larger cosmic pattern. To fully understand how far a human can travel in one lifetime, it helps to step back and place that lifetime within the broader timescales of the universe itself. This shift in perspective does not change the physics, but it changes how the limits feel. A human lifetime, even a long one, is measured in decades. At most, it approaches a century. In everyday life, this feels expansive. It contains childhood, learning, work, relationships, and rest. It feels complete. In cosmic terms, it is almost nothing. Earth is about 4.5 billion years old. The Sun will continue shining for another 5 billion years. The Milky Way galaxy has been forming stars for more than 10 billion years. These numbers are not dramatic exaggerations. They are ordinary measurements in astronomy. When distances in space are large, they are often large because the universe has had immense time to spread matter apart. Stars drift slowly, but they drift for billions of years. Galaxies move, but they move across spans far longer than any biological life. human travel is constrained not only by speed, but by mismatch. Our lives are short compared to the processes that shape cosmic structure. Even if we moved continuously at high speed, the universe is not arranged to be crossed quickly. This is why even the fastest probes appear patient rather than swift. Voyager does not rush toward interstellar space, it glides. Over decades, it barely leaves the Sun's neighborhood. This is not because it is slow, but because the scale it is moving through is enormous. From this perspective, the question, how far can a human travel in one lifetime, becomes clearer. The universe does not offer many destinations that fit neatly inside a human time span. Most meaningful distances were set by processes that unfolded over millions or billions of years. This does not make human travel insignificant, it places it. Human journeys are local by cosmic standards. They occur within tiny regions of space that happen to align with our limited time. This also explains why exploration takes different forms at different scales. Humans explore locally with bodies. We explore distantly with instruments. Telescopes and probes extend perception across time and space far beyond where bodies can go. So time, like distance, sets a quiet boundary, not because it is hostile, but because it is vast. The universe is old, and it moves slowly. Human lives are brief, and they move quickly only in comparison to one another. Recognizing this helps soften the question. It shifts it from frustration to understanding. Humans are not meant to cross galaxies. We are meant to understand them. As we continue, we will explore a related idea, that distance in space is not only about travel, but also about information, and how this changes what it means for humans to reach far places. When physical travel reaches its limits, something else quietly takes over. Information continues to move, even when bodies cannot. This distinction changes how humans interact with distance in the universe. Information travels through space primarily as light. Photons carry images, spectra and signals across vast distances without needing life support, shielding or rest. When astronomers study distant stars and galaxies, they are not travelling there. They are receiving information that has already made the journey. This matters because information moves at a speed no human body can approach. Light crosses the distance to the Moon in a little over 1 second. It reaches Mars in minutes. It arrives from nearby stars in years, and from distant galaxies in millions or billions of years. Through information, humans already engage with regions of space that are physically unreachable within one lifetime. Telescopes allow us to measure the composition of stars, the atmospheres of distant planets, and the structure of galaxies far beyond our physical reach. In this sense, human presence in space is layered. Bodies move slowly and locally. Instruments extend perception far beyond that. Understanding does not require physical arrival. This reframes the idea of distance. Physical distance limits where humans can go. Informational distance limits what we can know. An informational distance can often be crossed even when physical distance cannot. Space agencies rely on this distinction. Probes travel where humans cannot, and send back data. Telescopes remain near Earth and look outward across time. These approaches allow exploration to continue without requiring bodies to endure hostile environments for decades. For a human lifetime, this is crucial. It means that the meaningful reach of one life is not confined to the kilometers the body travels. It includes the information the mind can receive and interpret. A person may never leave Earth, yet understand the life cycle of stars, the structure of galaxies, and the age of the universe. In contrast, a person may travel millions of kilometers in orbit and still remain close to home in informational terms. So when we ask how far a human can travel, we must be clear about what kind of travel we mean. Physical travel is constrained by time and biology. Informational travel is constrained mainly by technology and patience. This does not diminish the value of physical presence. Being somewhere allows interaction, experimentation, and experience that information alone cannot provide. But it does explain why human exploration naturally divides into two modes. Within one lifetime, bodies explore locally, minds explore far. As we move toward the final sections of this exploration, we will gently connect these ideas back to the human experience, not as a limitation to be mourned, but as a pattern to be understood and accepted. There is something quietly important about the fact that humans can observe regions of space they will never physically reach. This is not a failure of exploration. It is a feature of how intelligence interacts with scale. When you look at a star in the night sky, you are not seeing it as it is now. You're seeing it as it was in the past, sometimes thousands of years ago. Light has travelled across space and time to reach your eyes. Without moving your body at all, you are receiving information from far beyond any possible human journey. This creates a separation between experience and understanding. Human bodies experience space locally. Human minds understand space globally. That separation can feel frustrating at first. It is natural to want presence, not just knowledge. To want to stand where something is, not only to measure it, but in the universe, presence is expensive. Understanding is comparatively cheap. Science emerged as a way to work within that imbalance. We learned how to let information travel for us. We learned how to build instruments that wait patiently, collect faint signals, and send them back across space. We learned how to reconstruct distant environments from subtle clues. In doing so, humans extended their reach without extending their bodies. This matters for a human lifetime because it aligns exploration with biology. A single life can absorb vast amounts of information. It can study stars that formed before Earth existed. It can understand galaxies whose light began travelling before humans evolved. No spacecraft journey could do that within one lifetime. This does not make physical travel unimportant. Physical presence allows direct interaction. It allows us to test materials, examine surfaces, and experience environments in ways that instruments alone cannot. But it does suggest a balance. Human exploration is strongest when bodies go where they must, and information goes where bodies cannot. This balance is already visible in how space exploration is practiced. Humans stay close to Earth, where rescue, communication, and support are possible. Machines go farther, where time and distance stretch beyond biological tolerance. Within one lifetime, this approach maximizes understanding while minimizing risk. It respects both curiosity and constraint. So when we ask how far a human can travel, the answer depends on which part of the human we're talking about. The body travels millions or billions of kilometers at most. The mind, through information, ranges across the observable universe. Recognizing this distinction allows the question to soften. It no longer feels like a door closing. It feels like a shift in method. As we move on, we will look at how this layered form of reach shapes human meaning in space, not through conquest or expansion, but through continuity and understanding. The most far-reaching human journeys do not involve humans at all. They involve machines built to carry curiosity rather than life. Probes like Voyager, New Horizons, and many others are extensions of human intent. They go where bodies cannot, not because humans are unimportant, but because biology has limits that silicon and metal do not share. These machines do not replace human experience. They amplify it. A probe travelling beyond the outer planets still belongs to Earth. Its design reflects human decisions. Its instruments answer human questions. Its data becomes part of human understanding. In this way, human reach extends far beyond human presence. Telescopes do the same thing without moving far at all. From Earth orbit or from the surface of the planet, they collect light that has travelled for millions or billions of years. They allow a single human lifetime to contain knowledge of cosmic processes that unfold far beyond that span. This is a quiet kind of travel. It does not involve engines or trajectories. It involves patience, interpretation, and care. Importantly, this form of reach fits naturally within a human life. A scientist can spend decades studying a class of objects and gradually build understanding. Each year adds depth rather than distance. Knowledge accumulates without demanding physical endurance. This pattern appears again and again in science. When physical limits are reached, abstraction and measurement take over. This is not a retreat. It is an adaptation. For space exploration, this means that the most meaningful expansion of human presence may not be measured in kilometers travelled by bodies, but in regions understood by minds. A human who never leaves Earth can still participate in the exploration of the universe. They can analyze data from Mars, from the outer solar system, from distant galaxies. Their contribution is not diminished by their physical location. So within one lifetime, the question of how far a human can travel has two answers. One is bounded and modest, the other is vast. The bounded answer tells us where bodies can go safely. The vast answer tells us where understanding can reach. Together they form a complete picture of human exploration, one that respects biology, embraces technology, and aligns curiosity with reality. With this in mind, we can now begin to return gently toward the question we started with, bringing these insights back to the scale of a single human life. We began with a simple question: how far could a human travel through space in one lifetime? After moving through speed, biology, technology, and scale, the answer is clearer and calmer than it first appeared. A human body, protected and supported, can travel intentionally within the inner solar system. The Moon is reachable in days. Mars is reachable in months. Repeated journeys might span decades. With extreme assumptions, the outer edge of the solar system might be approached but not returned from. Beyond that, distance grows faster than time allows. This is not because humans lack ingenuity. It is because human lives are short compared to the structure of space. The universe was not shaped with human travel in mind. It follows its own rhythms. Seen this way, the limits of travel do not feel arbitrary. They feel proportional. They match the scale of a life to the scale of a neighborhood. Earth and its nearby planets form a region where human presence is possible. Beyond that, observation replaces presence. This framing removes urgency. It suggests that there is no race to cross the universe. There is time, not for bodies to travel far, but for understanding to deepen. So the answer to our question is not a single number, it is a shape. A region of space within which a life can unfold without being overwhelmed. As we continue toward rest, we can let go of the need to go farther. The universe does not require us to reach it physically to be meaningful. Distance in space is often treated as a measure of achievement. Farther is seen as better. But from a human perspective, Distance becomes meaningful only when it fits within experience. The moon is meaningful because humans have been there. Mars is meaningful because it can be reached and studied directly. These distances align with planning, memory, and return. Beyond that, distance becomes abstract. The outer planets are real but remote. The stars are visible but unreachable. Their significance comes not from proximity, but from understanding. This distinction helps explain why exploration feels different at different scales. Close exploration is embodied. Distant exploration is intellectual. Both are valid, both are human. Within one lifetime, meaning tends to concentrate near home. This is true on Earth, and it remains true in space. We invest in places we can visit, return to, and relate to. This does not make distant places less important. It simply changes how we engage with them. So when we ask how far a human can travel, we can also ask how far meaning travels with us. Often, it travels best when distance is moderate and connection is strong. This perspective brings us gently back to stillness. Travel does not always require motion. Understanding can arrive without departure. Even when humans do not move far, they are never truly still. Earth continues to turn. The planet continues to orbit. The solar system continues its long path through the galaxy. Every human life is carried through space whether we choose it or not. This motion is quiet and constant. It does not demand attention. It does not exhaust the body. It simply happens. Recognizing this can be calming. It reminds us that we're already part of a journey larger than ourselves. We do not need to go anywhere to be moving through the universe. In one lifetime, this motion carries us immense distances, but more importantly, it carries us through time, through seasons, changes and cycles that give shape to experience. Space does not require conquest to be meaningful. It requires awareness. As we rest, it can be enough to know that we are already traveling, already included in the vast patterns of motion that define the universe. We began by asking how far a human could travel through space in one lifetime. The answer is modest in distance but complete in context. A life fits within a region. A mind reaches beyond it. Both are enough. There is no urgency to cross what cannot be crossed. There is only continuity, motion without strain, understanding without pressure. Everything flows. Sleep in that motion.